Okay, so let's start with this short introduction to the school and to the topics that you will see during this week. And let's start talking about concentrating solar thermal energy, concentrating solar thermal systems, which are the topics of the school. And the idea, as you know, basically is to concentrate solar radiation through a system of mirrors. And in order to achieve high temperatures and collect high temperature heat, which as we will see later can be used for many purposes. So the idea, as you may know, is dates back from like 214, 212 before Christ, and it is attributed to Archimedes, and who is said to want to exploit this concept to burn Roman ships during the siege of Syracuse. So probably this was not done at the time, but the idea was there for sure. He got to burn Roman ships for sure, but probably with other means, not using sunlight, but the idea was there, it was written, and during the centuries it was developed. We have many interesting historical development of this concept through the centuries, which we don't have actually the time to discuss today. But I will, you will get these slides. So if you want to know more about these people who, as you can see, built the first heliostats or solar dishes. We have other very interesting pioneers who have found applications for concentrating solar energy in the 19th century for instance, for making ice, and this was kind of surprising at the time. Until I would like only to focus a little bit on this particularly important experience at the beginning of the 20th century, where basically the first, I would say, modern solar trough plant was built in Egypt. We're talking about the first decades of 1900, and this plant was built in Egypt to, it was basically what we call today a direct steam plant, so concentrating solar trough were used to vaporize water, and this high temperature steam was used to power a pump to pump water and use it for watering the fields in Egypt. Unfortunately, we had some wars in between that period and today, so this first experience was like wiped out by these unfortunate events. But today, this concept is now applied to industrial plants for many different purposes, and this is the object of our course. And the outline of this presentation is basically the schedule of this course, because this is what you will see this week. We'll start today with a short introduction to the whole topic. You will have some insight on the role the concentrated solar thermal energy can have in the future energy system of the world, what advantages this technology can bring in terms of environmental benefits and also economic benefits. Then we will start from the basis. So you will follow all the topics. You start from the very first input you have to your process, the solar energy. So you will have a lecture today on solar resource. What is the solar resource that we need for concentrating solar thermal energy that you will see it's different from the type of radiation that you use in like PV systems. And you will have you will go then, you start analyzing in detail all the four main concentrating technologies we have today. So parabolic trough, I would say in order of importance, so they are diffusion. But the order that you see is by total amount of installed capacity. So we start with parabolic trough, which is the mainly deployed technology today. Then central receivers, another type of technology which is catching up, however, with parabolic trough, because many of the new plants are built with this technology. Then linear Fresnel and smaller, somehow less costly, less efficient system that is, however, found in many interesting fields of application. And solar dishes, which are the most efficient but the least used, and probably you may, during the lectures, find out why. And then you will start, this is for the collection of solar energy, then you move to the use of solar energy, and we go to power cycles. So the main use we do today of solar heat, high temperature solar heat, is to produce steam, and then with this steam we produce electricity with conventional processes. And then we go to one of the most important features and features of this technology is thermal storage, the possibility of storing the collected energy with systems which are commercial today and allow to, in existing plants, to store energy up to 15 hours of the rated capacity of the plant, which means that today we're able, basically, with the appropriate conditions, to ensure continuous operation, even round-the-clock operation in some cases of these plants, by using this technology, which again is commercial. It's not something that we're studying, and it's rather, I would say, simple in principle, even if you see there are many more sophisticated applications that are under study by research. And it's viable today compared to electric storage with batteries that today basically is feasible up to 3 hours, let's say. Some reports say that, at least. And here we have storage capacity up to 15 hours in existing plants. And then we really want to know, you to know with this school that concentrating solar is much more than electricity. It's not only electricity. So we will have a lecture, a very short overview of other applications that are currently made with concentrated solar heat. Not only electricity, but also we already mentioned desalination, process heat, which is gaining an ever-increasing interest in the last period. And solar fuels, we can use this heat to produce fuels like hydrogen or more conventional liquid fuels. And you will see this later. And finally, how much does this cost? You want to know, today one of the main issues of this technology is related to cost. This is not a technology as mature as PV, for instance, and it's more costly today. So this higher cost is bottlenecking the development of the technology, so this is an important issue to be considered. So you will have an overview on the basics of CSP economics, but you will also see that the LCOE, the cost of electricity of production, it's only a part of all the economic aspects related to an energy technology. So this will be very interesting to know. And finally, you will get an outlook on what are the main trends today for research topics and commercial plants in this field. You see that during the afternoon, even because we know that having to follow frontal lectures like these for a whole day may be very difficult. So we managed to have in each day, especially during the afternoon, some hands-on activity. So you will get the chance to use some softwares which are available for free and for simulating either the ray tracing software or simulating the performance of CSP plants. So we think this is a valuable experience that you can have, and which will help you fix some concept that you will get during the lectures. So let's start talking about catching sunlight, concentrating it, and turn it into high temperature heat, and then other forms of energy like power or chemicals or desalinated water or whatever. So first of all, how do we collect today the solar and concentrate the solar energy? Basically, today we have four concentrating technologies, which may be classified by the type of focusing. We have line focusing systems, which, as the word says, concentrate the sun rays over a line, and in this case we put on this line a tube where we flow a heat transfer fluid, and we collect the concentrated heat in this heat transfer fluid, which is then moved to other parts of the plant. And then we have point focusing systems, in which, on the other hand, heat is concentrating on a point. So there we have a receiver, again, which is shaped clearly differently than it's not a linear tube. It will be probably a coil or something else. You will get a lecture on this, of course. And what is the main difference here? The main difference is about the concentration factor, which is basically the amplification factor of the flux density, the energy flux density that you can get with these systems. And very roughly, it may be associated with the surface ratio of the receiver to the mirror's surface that are collecting their solar energy radiation. So for point focusing, we can achieve very high concentration factors, even above 1,000. So we talk about 1,000 suns to say that the radiation is 1,000 times more intense, more concentrated over a surface than what we get from sun, directly from sun. In line focusing systems, the concentration ratio is usually below 100, may go from, let's say, 70 or 80 for parabolic troughs, and even lower for Fresnel systems. And then another way of classifying these concentrating technologies is whether we have or not a moving receiver. So as you will see later, we need a tracking system, and the concentrated solar thermal systems rely on a tracking system which moves our systems to follow the sun in its apparent motion in the sky during the day. It's very important that our receiver directly face the sun. We need what is called a direct normal irradiation to make these systems work. We cannot rely on reflected or diffused radiation. We need direct radiation from the sun. So our systems move during the day, and for sure the mirrors move to follow the sun, but the receiver may be fixed or move with the mirrors. So in static receiver systems, the mirror moves, and the receiver is not moving. And moving receiver, in systems with moving receiver, the receiver moves with the mirrors. So let's see some pictures which make clearer what we're talking about. First of all, we talk about solar dish. Solar dish, as you see, it's a parabolic surface, which concentrated the radiation over a point where we put a receiver. So in this case, the whole thing moves to follow the sun during its apparent motion, and as you can see, both the mirror and the receiver move at the same time. This entails also, in general, a higher efficiency, because we are always sure we always have the best alignment of the receiver and the mirrors. And not only that, also the fact that the receiver is close to the mirror is also another important aspect which affects the efficiency of the system. And basically, also in this case, you see that we have the receiver close to the mirror. So the dish is the system that combines some of the best features to obtain the highest efficiency, and indeed today it holds, this concentration system holds the record in this field for converting solar energy into power. We're talking about something in excess of 32%, but this is not without any other issues that you will see in the lecture devoted to solar tissues. It's very interesting here to see also an anticipation of what other applications concentrated solar energy are. Here you see what is called solar cooking application, which may seem very simple or not as important as producing electricity with big power plants, but I can assure you that also this type of application, simpler application, may have an important impact on society, on environment, and especially in developing countries. So this is also an important market, a possible market for this system. there is a market for this type of system. Central receiver system, again, we're talking about point focusing systems. In this case, we have a central receiver, which is usually located on top of a tower, which may be hundreds of meters high. And it's not moving, of course, so it's fixed receiver. And then we have the solar field that's constituted of a set of heliostats, which are mirrors, flat or slightly curved mirrors that move, tracking the sun on two axes like dishes. Also, dishes can track the sun on two axes during the day. And all these mirrors point the radiation towards the receiver. So here you collect the concentrated solar energy, and you can collect heat at high temperatures. Then we move to the parabolic troughs. Again, as I told you before, this is the technology that today makes up for like 90% of the total installed capacity of concentrated solar power plants. And in this case, concentration is along a line. So the system is constituted by parabolic mirrors that are curved only along one axis, while they are linear on the other axis. So the section, the cross-section of the mirror is a parabola, which has focal properties, and all the straight rays that come on this acceptance surface of the mirrors are concentrated on a point here, which turns into a line if we move from the cross-section to the actual 3D structure of the system. And in this case, the system can track the sun only along one axis. So as you can see here, during the day, the system will move this way. And again, concentrate the solar radiation along a line. Here, the concentration factor is maybe around 70 or something like this. And finally, linear Fresnel, which are gaining an increasing interest. You will get the chance to see a Fresnel plant which is installed on the top of the building next to this one. So during the coffee break, you may already have probably a sneak peek from the windows. And on, I guess, Friday, we'll see, you will visit it. And in this case, the principle is the same of Fresnel lens. This is what the name comes from. And again, I think that the figure is quite clear on how these single mirrors are inclined in a different angle in order to concentrate the solar radiation on the tube, again along a line. The receiver is fixed, and usually the receiver is equipped with a secondary optics like this, which ensures that the radiation is collected on the tube and decreases the losses because of not perfect alignment with the tube as well. So this is how we collect and concentrate the radiation today. And now why we are doing this? What are the uses we make of this concentrated solar heat? So basically the principle in general of concentrated solar thermal energy, we talk about the acronym CST stands for concentrated solar thermal, which opens to a range of possible applications. So we have solar reserves. We use concentration systems like the ones you have just seen, and we focus the radiation on a receiver. Then we move the heat collected. This is basically the solar field. The heat collected is this way we produce solar heat, and you will see we also have the possibility of having thermal storage in this scheme. So what we do with this high temperature solar heat? We have a range of possible applications. Here I've just summarized some, the most important of which today is producing power. So these systems today are basically used to produce power, but there are other applications which are gaining day by day more important. We mentioned desalination. We can use heat to power thermal desalination processes. This can be combined also with power production. This is important. Here you have a range of applications. You don't have to necessarily have just one. Sometimes you have what is called polygeneration. You produce more than one product at the same time. So you may produce power and desalinated water. I will show you an example of this. You can produce heating. When we say heating, it's clear. We're collecting heat, so we can directly use this heat. Either for process heats, when we have high temperature heat like 4,000 degrees or even higher, above 800 Celsius degrees in the most recent applications. You can use this heat in industrial processes, which are used to produce commodities or any other product. You know, many processes require high temperature heat, like mining industry, or also in oil and gas industry. There are many processes that require high temperature process heat. You can provide this heat with solar energy. This is clean, renewable heat. But when we talk about heat, we also think about residential applications, so buildings, heating requirement during winter time for building. And at the same time, since we're talking about, on the other hand, with similar approach, we may have cooling, industrial cooling for processes which require low temperature, or residential cooling. And the Fresnel plant you will visit on Friday provides both heating and cooling for buildings. So it's an application that you will see in an existing installation. And finally, last but not least, and in solar fuels, this has been my main object of study as a researcher, so I'm really interested in this application. We may think about this as another application of process heat. So you use solar heat into a chemical process, which is used to produce mostly today hydrogen, but also other fuels like synthetic methane, so synthetic natural gas basically, or liquid fuels produced again using high temperature heat, and water and carbon dioxide. So there are many applications in this field, and it's very important because this is also a way of, how to say, bottle solar energy. We may think at countries like Australia or Chile, which have a high abundance of solar reserves. They produce a lot of energy. They produce more energy than they require in their own markets. They may be interested in exporting this resource that they have. So if we find a way of converting this energy into another energy vector, an energy carrier, like a chemical or a fuel, we can then export this fuel to other countries. So this is an important application for these systems. But okay, here you see also first application scenario for a different type of concentrating technologies that we have seen. So which technology is best suited for any application? It depends. It's mostly related to the temperature level it's required by your process. So if you go above 500 Celsius degrees, we're talking about concentrated solar power and high temperature process heat. 250, 550 Celsius degrees. Here we are in the range of the so-called high temperature process heat. So again, centralized power production, high temperature process heat. And then we go below. As we move from the top to the bottom of this list, we have lower concentrating factors, lower temperatures, and different applications. In this very low temperature range, we probably don't even need any concentration. We just use solar heat with flood collectors, which are not the object of this school, of course. Then compound parabolic collectors are, again, you have a very small concentration ratio, which is not covered again by the school. This required for solar cooling and heating and low temperature process heat. And then from here above, basically, we are within the scope of the school. So when we use more sophisticated tracking concentrating system that will allow to get more efficient solar heat and higher temperatures. So we mentioned, however, that besides this wide range of applications, there is one application that today is dominating the market of this system, and it is power generation. So what is the basic concept of using concentrated solar thermal system to produce electricity, which is today also the strength of this system compared to other renewable electricity production systems. How do we produce electricity today? I guess all of you have more or less a technical background or engineering background, so you know that basically we produce mostly energy through thermal processes which involve burning or using some fossil fuel to produce heat, and this heat is used to heat up a working fluid, be it a gas or be it steam in steam cycles, and we use this steam in a thermodynamic cycles which converts this heat into power in a thermal power station, usually centralized. Of course, the drawbacks of this approach are related to environmental problems that you have, mostly the high emissions of CO2, of course, which are not only the time where you burn these fuels, but this high amount of CO2 are also produced at the time in which this fuel is produced from the wells, from the reservoir where the hydrocarbons are stored naturally. So the basic idea of what we call concentrated solar power in this case, not concentrated solar thermal. When we say concentrated solar power, we are specifically talking about this application of producing electricity out of concentrated sunlight. The idea is just to substitute the burning fossil fuels with use of a high temperature heat. So we use this high temperature heat that we collect with a concentrated system to produce steam, for instance, and directly use this steam at thermal power station. Okay, I will skip this. This is a comparison of these main technologies for application, but I will really running out of time because we will get the first lecture very soon, I guess. Yes, so I will move forward. And of course, in this process of converting the solar energy into electricity, we have different fluids are used, at least a maximum of 3 materials, I would say, is a heat transfer fluid, which is used to collect the heat and the solar field and move it to the user, for instance, from the steam generator in your power block. You will have a fluid in your power block, which is the working fluid of your thermodynamic cycles, maybe water, steam in the case of a Rankine cycle, and maybe air or a gas in the case of a Brayton cycle, a gas cycle, and so on. And finally, we mentioned several times the thermal storage. You may have a material which is used to store your heat and use it when the sun is not available. Okay. In some cases, this fluid may also coincide. So we will have a system in which the heat transfer fluid is the same as the working fluid of your working cycle, or your thermodynamic cycle. You will see this especially in the dish lecture, where you will use air as heat transfer fluid in the receiver, and this air is the working fluid of the thermodynamic cycle used to convert heat into electricity, for instance. You may have the same fluid for collecting heat in the solar field and storing energy, as in direct storage, so-called direct thermal storage systems, where you heat up a fluid and you store this fluid to store the energy collected, and so on. So these fluids may be different. Okay, here I also included some information of heat transfer fluids, but I will leave it up to a specific lecture to talk about this. I just want to tell you that today there are several options that are studied, even if basically the heat transfer fluid in the solar field, we use mostly liquids. We use only liquids in the existing plants. Commercial plants, sorry, because there are also demonstration plants which use of other fluids that are here. So the most used are thermal oil, which is a heat transfer fluid very well known by the process industry, and also pressurized water and molten salt. Molten salt, this is a particular heat transfer fluid. It was developed within the nuclear industry, but it's now very, very important to the field of concentration of thermal energy. It's a mixture, the most commonly used molten salt system is a mixture of potassium nitrate and sodium nitrate. It is stable up to slightly below 600 Celsius degrees, even if it's used up to 565 Celsius degrees. It is stable at ambient pressure. You don't need to pressurize your lines to keep this system liquid. This is the strong point. This is why we want to use this. The drawback is the relatively high solidification point, which is about 200. This mixture starts to solidify at about 240 Celsius degrees. So this means that we will have problems for freezing prevention in the plant. As you can see, besides these ones that are most used, also two-phase system, water steam, direct steam systems, you vaporize the water directly in your solar field. There are other heat transfer fluid that are being considered, like gases, atmospheric air, compressed air, compressed CO2, even solids. How do we use solids? Like sand or granular solids, which are fluidized and sent to the receiver. And the advantages in this case is clearly they are cheap, they are safe, we don't have freezing problems, but at the same time there are other types of issues like friction problems on the surfaces and so on. Also, it's not that easy to move these solids around the plant, and at least it's not as easy as moving a liquid or a gas, as you may easily understand, and so on. So there is the research in this field is very active, even if, again, these other heat transfer fluid are not implemented in commercial plants. Okay, here are some more information. We don't have time. So just a word on the efficiency. We mentioned efficiency. I told you before something about 32% as the record efficiency in converting energy from the sunlight to electricity. But what is this? What we mean with this efficiency? What is the denominator of this ratio that we use to calculate the efficiency? So basically, usually you take as the input energy the DNI. You will see later what DNI is, collected by the mirror surface. So this is the input energy to your process, what you have here. And then here it's easy, the power produced by your system. So what is in between these two points, and what are the causes of losses of energy? You have losses at the concentrator level, because of course not perfect optical properties of the system, not perfect reflectance, imperfection in the geometry of the mirrors, not perfect alignment of the receiver with the concentration system and so on. Tracking errors, so you're not exactly pointing your system to the sun. Cosine losses you will see later. Shadowing effect, in some cases some of your concentration elements are in conflict with each other, so you may have, for instance, one heliostat shadowing during specific times of the day, another heliostat, and so on. And losses, this you will see when you will visit the plant, especially this is for linear concentration systems. Receiver, you will have losses at the receiver level, again, reflectance, re-radiation, losses by convection, losses by conduction to the structure of your receiver. You will have some heat transfer, losses at the heat transfer level. Of course, your pipes are not perfectly insulated. You may put as much insulation as you want, but you will have some losses. Here, however, the losses are really small compared to other ones you have seen in this list. Also, a thermal storage system, which basically is a tank, an insulated tank where you store hot fluid, will have losses to the environment. So here the losses, however, are like 5%, it's very small, important, as you can see, are in other stages. And finally, the power block, because besides the inequalities, non-idealities of the power block, you will have, of course, conversion of heat into electricity, as you know, is not possible 100%. You will have the efficiency of your power cycle, your thermodynamic cycle. and you will, which you know cannot exceed the Carnot efficiency depending on the temperature level. So the higher the temperature of the collected heat, the higher will be the efficiency of the thermodynamic systems, of course. But you will have thermodynamic losses there. Here there is a table which is actually a little bit old, because the source is ENEA in 2013, which you have a comparison of different technologies that we have mentioned. I would suggest not really sticking to the figures, but so not really quantitatively, but most qualitatively the comparison here is correct. So let's talk about efficiency. We have defined efficiency in the previous slide, and I told you that the record of efficiency is like something in excess of 30%. There we're talking about the peak efficiency, the maximum efficiency that you can get with that system when the conditions are perfect. You have a high radiation, you are exactly pointing towards the sun and so on. But during the day, the efficiency of your system varies, because when the sun is not high over the horizon, you will have lower efficiencies of your system and so on. And especially when you talk about the peak and instantaneous efficiency, you're not talking about what is the average efficiency you have during a year. During a year, you will have the resource. The resource is not available 24 hours a day, and there are periods in which your plant is not operating because of regular maintenance and so on. So the average efficiency of your system is lower, much lower than that. And just to have an idea, the average efficiency of the commercial plants today is around 15%, yearly average efficiency. And here you see 14%, something in excess of that. The most efficient plants are probably those who use direct storage with molten salt. You will see later what this means. So basically it means that you use molten salt as heat transfer fluid and storage systems. This allows you to operate your system at higher temperature, which means higher conversion efficiency with thermodynamic cycles, and also lower losses for heat exchanger, intermediate heat exchangers, and so on. Okay, so again, the concentration, we already mentioned what are other different like concentration factors, which are higher, of course, for point focusing systems, and the highest are for dish systems. Okay, just a few words on now we said how we collect energy, what we do with this collected energy, when we can, where we can do this. This is not a technology suitable for any place in the world. And the reason why is that, of course, we rely on solar energy, but on a particular component of the solar radiation, which is called the direct normal radiation. So the radiation that comes directly from the sun. So we cannot use diffuse radiation from clouds, for instance, or reflected radiation. Later today you will go into the details about this. And this means that there are a lot of reasons why the direct radiation is also attenuated by the atmosphere, by humidity in the atmosphere, other factors you will see today. So basically, this technology is suitable for places where we don't have many clouds, during the air is not humid. So here you have a world map of the ENEA, and you see that, for instance, we may think that the equator, we have the highest, the sun is the highest position over the horizon during the year. But as you can see, there are several regions around the equator which are not suitable for this technology. The reason why is that there are a lot of clouds, lots of rain there. The air is humid, so it's not very suitable for this technology. And also, when you operate very close to the seaside, you have the similar problems. What are the suitable regions? Basically, you see here deserts in Chile, in Australia, in the deserts in the United States. In general, desertic areas, especially located in high mountains, are very well suited for this technology. Here we have, in Chile, in the desert of Chile, you have the highest ENEA in the world. So, okay, this is more or less the same. So this is reflected in the current market of this technology. So the plant are basically today, half of the total installed capacity, we're talking about roughly 5 gigawatts. Half of this, roughly half of this capacity is in Spain today. And there are political and historical reasons why, probably Manuel will talk about this later, I don't know. So Spain today is the country where we have this technology has been deployed the most. Then we have also United States, of course, where the first, I would say, commercial plant had been built, starting for the half 80s. And very important now, the emerging markets, not more emerging, not any longer emerging, but actual markets in Morocco, in the ENEA region, and China, which is now becoming a very important player in this market. Also South Africa, which are all regions that you can see match the map of the ENEA that we have seen before. What are the technologies in operation today? I told you before that roughly 90% of the overall installed capacity is made by parabolic shafts, but now there are many of the plants under development or constructions are now based on the central receiver technology, so these are the technology. And also Fresnel systems are gaining an increasing interest, even if they are still far from having the number of installed capacity that the other technologies have. Dishes for the moment, basically, we don't have any big installation. We have 2 plants which are not now not operating any longer, but you will know more about these systems, what are the pros and cons of this technology during the lecture devoted. So, and finally, just one word, the important feature is thermal energy storage. The concept today is very simple, I would say. So we use, when we have excess solar heat from the solar field, we just store this heat with a sensible heat by heating up a liquid, molten salt in commercial. This is the only commercial solution for thermal storage today, even if we will see on Thursday, research in this field is very active. This is now one of the fields of research in concentrated solar thermal systems which is more active, because it's very important to reduce also the cost of this part of the plant. And the idea is very simple. When we have excess solar heat, we heat up molten salt. We store this molten salt in a hot tank, which is at around 550 or 565 Celsius degrees, depending on the technology. And during the night, we just use the heat stored during the night. When we don't have solar radiation, we use this energy from the hot tank to continue the production of our plant. So there are 2 approaches, direct and indirect. We'll go into the detail of this on Thursday. The important point is that this allows for in existing plants up to 15 hours of operation at the rated capacity of the power block. This means that there are plants that have been operated like for more than 30 days continuously without stopping the production, even if, of course, at night you don't have any solar source. And as for the cost, I will let this topic to be faced on Friday's lecture. So now I will stop my introduction here and leave the floor to Professor Blanco, who will tell you about the role of this technology in the energy system of the future, especially. What are the benefits that the deployment of the technology can bring to the energy system. So, thank you very much.